Okay, so video 3 of week 2, focusing on model, forecasts, and analyses. So, as a general starting point, you may have gathered this so far. I'd like to start with sort of a high-level just description of what the thing is that we're talking about. And if you go to the very generic sense of what a model is, of course, not even considering meteorology, a model, by definition, is any simplified representation used to explain the workings of a real-world system or event. And that simplified representation idea, we've talked earlier this week. We talked about station models as a way to represent the surface observations graphically. So again, we're making a simplified representation to represent the real-world observations that we're getting from our surface stations. However, that's sort of a data model or an information model, a representation of some data set. If we're talking about, though, a weather model, like when you hear the models forecasting this in sort of a TV forecast or an online forecast that you may hear, those are numerical simulations. So they're directly simulating state variables, pressure, temperature, humidity, all things of that sort, and dynamic variables, really meaning wind and things related to the movement of the air, simulating those variables of the atmosphere and how they evolve over time. As sort of represented by this figure here, this is a very high resolution model. This is a tornado vortex research model, essentially. But you can see that it's really simulating fluid dynamics. It's not just abstractly describing the way it theoretically works. It's not performing some kind of statistical fit. No, it's actually representing, in a numerical sense, the motions of the fluid and all the vortices and all the intricacies of what's going on. Of course, not every model looks like this. In fact, no operational model are anywhere near this resolution because we can only compute so much and we can only observe so much. So we're limited. We choose to be limited in order to make it a feasible problem to actually run these models. We're limited by the scale or the resolution of what we can represent in these weather models and the complexity of the equations we choose to use, because the full expressions for the equations that represent the atmosphere, they're just simply too complicated to be completely and fully represented. We have to make some approximations along the way, which reduces our complexity, but makes it a feasible problem. It makes it simplified enough to be able to run them on supercomputers, because if we tried running everything, we wouldn't even be able to run it on the most powerful computers in the world. Another thing to clarify, and this is a common source of confusion by those who aren't used to the field of meteorology, is that this isn't a statistical model either. We aren't looking at input variables, performing some kind of statistical fit, some sort of equation, finding coefficients, and then whenever we get new variables, plugging those into that statistical fit and seeing what our output is. That isn't how weather models work. That's a statistical model. And there are certain pieces of weather models that maybe run that way as a part of the simplification of those equations. But an overall weather model is a numerical simulation. We're actually trying to resolve the physical properties of the atmosphere through these numerical simulations, not just fit inputs to outputs to try generating a forecast. So going into a little bit of history, just to sort of see where things have come from. Wilhelm Birknes, sort of late 19th century, early 20th century, referred to as the father of modern meteorology, was the one who is credited with first deriving the fundamental equations of motion for the atmosphere. These are based on the Navier-Stokes equations, really sort of well-known problem, but also a very complicated problem in classical physics. But applying them to the gases and things that we observe in the atmosphere, that's credited back to Birknes. Now, Louis Fry Richardson sort of followed up on that in the realm of weather modeling, was the first one to attempt to apply those equations, because they're a set of differential equations. So trying to apply those differential equations to actually forecast the weather. Of course, back when he did this in the earliest part of the 20th century, we didn't have satellites, we didn't have radar, we didn't barely even had surface observing stations. We didn't really have much for upper air or anything like that. So it was very basic, very primitive, but it was attempted. It didn't work out real well. The forecasts were nowhere near accurate, and they took several months to forecast ahead a few hours or days. But the proof of concept is that you can actually apply the mathematics in order to solve for a forecast. And based on his experience and the fact that there weren't computers around at that time, other than people who actually computed things by hand, he envisioned massive lecture halls and conference halls of people just working away at equations, solving their little portions, passing it off to the next person, and this massive thing to coordinate. Of course, that never happened because computers, as we know them today, were developed. Even the very first computers, one of their tasks was to motivate them was weather modeling. So ENIAC, one of the very first computers that's seen common use that had enough power to do this kind of thing in the 40s and 50s, implemented the first computational models. So instead of, individual humans computing their little portion, you instead have computer processes, things running, and these can be scaled up and run in parallel, and both in parallel and series, one after another, in order to depict what's happening around the world. Of course, these were very, very simplified models compared to what we're running today, but they were useful enough by the 50s that they came into operational use, that they actually started using these in the process of generating forecasts, rather than old techniques of understanding broader scale patterns and just sort of extrapolating their based on their understanding of these systems forward in time. We're instead actually predicting the physical nature of the atmosphere in future times based on computations. And since the 50s, there has been continual improvement decades since. Instead of just representing the very broadest of waves in the atmosphere, we now can almost run global scale simulations that can pick up on fine scale details of weather systems. And they're a lot more accurate. And that goes to show how much effort has gone into the field of meteorology in the decades since, in observations, in physical understanding, in computational advances, and all of that. So getting into the basics of how a weather model works, I like to think of it sort of as these three categories. We have to start somewhere. So we start in real observations to get an idea of where we have to start off a weather model. Then there's a lot of math, a lot of math. We won't be talking about the details of the math in this course at all. If you want to, you can take several courses in numerical weather modeling and all the foundations needed for that to understand the mathematics. We're not worrying about it here. If you're interested, feel free to contact me though. And then the goal of that is to end up with a forecast, and then something we can actually look at to say what the weather is going to be like in the future. So observations, these are a lot of things that we've gone over earlier in this week, or will be going over in the last video. So these include surface stations, buoys over the ocean to fill in the gaps that we have in our regular surface obs, or our upper air observations from radiosondes. They're actually, the one thing I didn't touch on in our upper air section is that they sometimes fill in those gaps with airplanes because, we have these mechanical objects that we're controlling and flying through the atmosphere. We might as well take some data. And they need that data for flight operations, so we might as well use it for other purposes as well. Then we also have the other two most common remote sensing techniques, using satellites in some form of Earth orbit, and then weather radars mounted on the ground surface, which scan using microwaves. So that's sort of our first step. We need to gather the observations. Then sort of the first step of the lots of math step is that we have to create an analysis or initial state for a model. So we have all of these different observations. They're on their own points. They're scattered in space and on not any sort of regular representation. We have to bring those in and combine them all together into something that makes physical sense so that the equations of motion that we're going to use to predict the weather have a physically reasonable and stable starting point. Otherwise, the equations will blow up and we won't get a useful forecast at all. In addition, the models have to represent either on a regular grid all these data points so it can actually represent it on a computer, or some other models represent, instead of discrete points, they represent combinations of waves. If you've ever studied math or physics, like Fourier transforms, we apply similar ideas, instead represent waves rather than discrete points in the atmosphere. But regardless, we need to create this initial state to verify our physical reasonableness. We fill in gaps in observations, and we have to have some way to represent all of this on a way that the model can work with. So the second step of our lots of math portion of weather modeling is that we have to use predictive equations. And in a very, very simplified sense, this is what those equations look like. That we have some change in an atmospheric variable over some time period. So this rate of change is equal to the sum of everything that causes A to change. It makes very intuitive sense. We consider how A changes to be equal to the causes of things that make A change. But what this does is that this is a discrete change in A. This is a discrete change in time. So what happens if we bring this over to the other side? We get something that looks like this, that now we're getting somewhere. Now we can say that our forecast of our variable is equal to our starting point plus the accumulated effects over time. So we say we have how much A is caused to change times over how much time that occurs allows us to have a discrete adjustment to A to go from our starting value to our forecast. And so what the weather model does is it has a bunch of these equations that are all interconnected. And step by step, little bit by little time, controlled, of course, to sort of balance how finely we can resolve temporal evolution against computational complexity and also stability of this numerical process. We go step by step, going from where we start for our variable to where we actually want to end up. Now, if you're, again, interested in the actual differential equations of all of this, you can find resources or contact me later. Not needed to worry about anything more complicated than this sort of basic rate of change idea, where we go from a rate of change to a stepwise process to go from a start value to an end value. So the last step in that sort of three-step process of weather modeling that I had up there is saving and analyzing the output. We actually have to do something useful. Model isn't useful if you don't use them. So in order to use this output, typically, even though there are other ways of looking at it, we most often analyze our data on isobaric surfaces of constant pressure. And that goes back to last video where we talked about upper air mandatory pressure levels. Part of the reason why we always want consistent observations on these levels is also because we look at our output of our weather models on these very same levels. And the great thing about weather models compared to observations is that because they have this full representation, this full numerical simulation of the atmosphere, really any atmospheric quantity can be available in the output of these models, from our typical state variables I've talked about a lot. Temperature, pressure, humidity, all of that. Dynamic variables, things like wind and things derived from wind like vorticity, but also other variables that we really care about in day-to-day weather. Things like precipitation and snow cover, reflectivity if we want, in our small scale, high resolution models, if we want a representation of what storms may look like, similar to, as we'll talk about in the next video, they look like on radar. We can also predict reflectivity values. We also can get cloud top temperature, so something that looks similar in the model to what we would see in satellite observations. All these kinds of things can be available in output. So to look at some examples, you may recognize this figure from the previous video where we talked about upper air observations. This is where that analysis idea comes in, is that sometimes we don't even need to right away use the forecast from the model. We just can use the model analysis in order to just fill in the gaps between our sparse observations in a way that makes physical, real sense. So we use a lot of analysis products as a way to fill in those gaps in a good way. We can also have things that look like this. This is a high resolution model, 3 kilometer grid spacing, so every discrete point is roughly 3 kilometers apart. So you can see here you have your wind, and this is 2-meter temperature, so surface temperature. We can see really interesting patterns over here once you start getting some topological effects and cloud cover. You see we're getting some cold temperatures coming in from the north. Not sure if that's your cup of tea or not, but it's coming. We can also look at broader scale flows. So this is 500 millibars, same level that we looked at the analysis product earlier, but this is on a hemispheric view, sort of top down looking at the globe as it rotates. And this, you can see these broad scale wavy patterns and these areas of high wind intensity. Wind is what's colored here. We'll be talking about large scale systems next week and what this kind of figure means. We can also, this is going back to that simulated brightness temperature, similar to what you'd see on a satellite. This is sort of a hurricane forecast, and it looks very similar to what you'd see in observations from satellite, but this is modeled, this is predicted, it's a simulation instead of what we're actually seeing. So with all of that, we come to the end of the video. Reminder, your discussion post, as regular for the reply, is due on Saturday. Hopefully you're able to get the actual post in. Of course, a number of you have added the course late. Hopefully you've heard from me or have seen on Canvas the appropriate adjustments to when you came on Canvas versus when your extensions are. Trying to give enough time. If it isn't enough, please do contact me. And really for anybody in the class, if you're struggling with anything, I want to be really accommodating with everything that's going on. I mean, I myself had to delay getting some of these videos together and posted, so I'm very, very understanding. If you need an extension, please just reach out to me. And if just a brief explanation, don't have to go into detail, just if you need it, reach out to me so that I know. I'd rather have you be a little late for a good reason than to mess things up and get a bad grade. Also the quiz, again, sorry for the delay in getting these videos up. Quiz is now due Sunday this week. I'll try to be doing better on getting things posted on time so we don't have to have any of these weird schedule modifications in the future. And then the final video for this week, coming up probably batched or very soon after this one, is on radar and satellites. So I will see you then talking about remote sensing in radar and satellites. Thank you.